Thank you for joining today. And this is Pipit Triani, and she's a finishing PhD student at Swinburne. Her principal advisor is Darren Croton. We all know if I pronounce the name correctly. Is her secondary advisor. And as I said, she's a finishing PhD student and on the job market. So I hope some of her applications are reaching you. And she practically included dust evolution into Darren semi-analytical model. So she did all that from scratch, and she will talk about that today and all the new work that she has done recently. So thank you again for being here. Thank you, Pipit, and take it away.
Thank you, Cami and Karthik, for inviting me, and thank you everyone for coming. During holiday, and it's not it's not a usual meeting time. So yeah, I am Pipit. If you find me in email, don't try to look for Pipit because it's Dian Triani. I'm Swinburne. I'm in Melbourne, so it's like morning and it's summer here. So today I will talk about my work. So my work focused on dust evolution. So I modeled dust in Darren galaxy formation model, and also currently I'm modeling dust in SED construction. Here is the outline of today's talk. After introduction and my science question, there's three major themes that I'd like to present. So first, I want to introduce you first to the new semi-analytic model. It is called DUSTICITY, which is the modification of Darren SAGE. It's in Croton 2016. So it runs on any n-body simulation with a formatted tree. So it can run on Bolshoi, Millennium, things MDPL is also good. But for my paper, I usually use Millennium because SAGE is well tested in Millennium. And for testing purposes, so for my newer work, I'm just testing it to the mini Millennium, so it doesn't take much time. Yeah, it is available on my GitHub repo. And the physics in DUSTICITY looks like this. So there's four main baryonic reservoir. There's pristine gas that will undergo infall to the dark matter halo, and it will be virialized into the virial temperatures. It's very hot. We name it hot halo in the model. There will be cooling from this halo reservoir to the interstellar medium. So now we have cold gas, which form clouds and become the site for star formation. Now, so there's a star formation activity in stars, because stars is the main production channel for metals and dust. So for example, smaller star will end up as AGB, and then it will expel metals that will later condense into dust. And more massive stars, for example, ends up as supernovae, which also expel metals that will later condense into dust. So the first dust production mechanism is the smaller.
Excuse me, can I ask a quick question?
Yeah.
I was very surprised that you're saying that you assume that gas comes in hot. Most star formation, at least until galaxies become quite massive, is fueled by cold flows. Are you not including cold flows?
Yeah. So the halo has the cold gas, but then the gas cooled down to the interstellar medium and forming clouds. So it's the usual cooling prescription.
What I'm describing is not cooling, and it's not the standard, the old-fashioned SAM approach is what you described. And
yes.
That's completely wrong. No simulations look like that. And as far as we know, no galaxies work like that. Is that really what you're doing? The 20-year-old SAM approach?
Yeah.
Where all the gas on the outside is hot?
Sadly, yes. Sadly, I haven't
just to clarify. All right. Thanks for clarifying.
No problem. Yeah. So sadly, I haven't really improved the cooling prescription, but there is a plan to do that. So in doing the newer approach for cooling, but now I haven't really touched the cooling prescription from Darren. So I just I work in the dust and star formation prescription more like that in the new DUSTICITY. All right. So yeah, so that's the first dust production channel. And supernovae can also destroy dust. So there's dust destruction by supernovae shocks. And dust can further grow in the dense molecular clouds via grain accretion. So the properties of dust in the interstellar medium is the balance of all of these processes. Now we also have feedback from the supernovae and AGN. So although I don't really have black hole and AGN in this picture, we have that in the model, which can reheat the gas to the halo. And if the energy is like still can't escape the potential well, then it can go out of the system into the ejected into what we call ejected reservoir. Now, because the temperature of the halo and eject is like really hot, dust can undergo further destruction via thermal sputtering. And yeah, this can further destroy dust. So the time scale for this sputtering is like very short. And the component, like the material in the ejected reservoir, so outside the system, can be reincorporated back to the halo, of course, like only a fraction, and then it can undergo like cooling back again and full star formation. So like all of this physics is modeled in dust stage. Now there are three main themes for my work. The first one is about the dust destruction in dust production mechanism in galaxies. So how do they compete to produce the observed dust properties? And the second is how does the dust content in galaxies evolve? And the last one is about the SED. So how does a shape change the shape of the SED? So to do that, I will use dust stage for the first and second question. And for the SED, I built a Python pipeline to extract the star formation and stellar metallicity history from the model to create the stellar spectrum, and then extract the dust history and couple it with the stellar light to derive the dust attenuation and infrared emission. So then we have UV to infrared SEDs for like millions of galaxies from the simulations that we can use to infer the observations. Okay, so about the dust production and destruction in galaxies. So here's this is a very, the pink one here is the famous star formation rate density. So the right axis here is the star formation rate density with redshift. So we see that the star formation rate, star formation history in the universe, like increasing with decreasing redshift until it reaches cosmic noon and then decrease again towards present time. The black line here is the analogical of that, but for dust. So this is the total dust production rate density, which is the result of the other three lines. So the green line is the formation rate in stellar ejecta, so AGB and supernovae. Blue line is the growth rate in the ISM, and a red line is the destruction rate by the supernovae. So what I am interested here is looking at the competition between the stellar dust and the grain growth. So dust that growth with via grain accretion. So we see here that in the early universe up till this redshift, so there's a switch here. It is the stellar dust that is dominate the galaxies. But after the switching point, the growth rate exceeds the stellar dust production by like almost 2 dex. Oh no, almost 1 dex. So this production channel affect the dusticity of the galaxy. The top panel here, so it's the same thing. So the dust rate density, but now plotted against the gas phase metallicity at redshift 0. So we see that for the metal poor galaxies, is the stellar dust rate dominates the total dust production rate density, while for metal rich galaxies, the growth that dominates. And if we look at the dust to metal, so the second panel is this dust to metal ratio, and the third panel is the dust to gas ratio. The trend before and after the switch looks like very different. So when formation in stellar ejecta dominates, it's either decline or like very slightly increase. But after the switch, when the growth starts, dominates, like it looks like increasing very sharp, and it reach a plateau where the grain growth almost consume like all of the metals in the dense. Here's the same thing, but now I plotted it against the stellar mass. So we see again, like for low stellar mass galaxies, it looks the same as the middle core, and for the more massive stars, like looks more similar to the middle core. So there's the trend. Also, does this stage reproduce the observed dust scaling relation at redshift 0? So we compare it again, observation of the dust mass to stellar mass relation, and we see that we can recover the increase, like dust mass increasing with stellar mass. It is also shown in like many observation. The red line is another model, and black line is the median of our model. So the color map here is the like individual galaxies in dusty stage, and we see that although the majority of the galaxies resides in this main relation, there's also like lots of galaxies like below this, like lots of scattered below the main line, showing the dust poor galaxies, which is the motivation for my next work.
Sorry, Pipit, Sandy has a question.
Yeah, could you just summarize extremely briefly how people are measuring the dust content that you're citing there?
Oh, it's the dust mass in the ISM. So I think it used the LCD fitting. So yeah, it's more like from the sub-millimeter and infrared survey. There's one from ALMA, I think. Okay. So we also find not only dust in the interstellar medium, but also, although the sputtering is very efficient, we still find like massive dust in the halo and ejected reservoir. So this is showing the dust mass density in the 3 reservoirs that we have. So the black line is the ISM dust, red line is the hot dust in the halo. It's not hot dust. In the dust, it's the dust in hot halo, and the purple is the dust in the ejected reservoir. So the point here is the observed ISM and CGM dust. So although halo is not like, I don't think like halo is like comparable to like IGM, it's like a good proxy for CGM. So we find like it's roughly agree with the observation. So yeah, the takeaway message from the first question is that now from the model at present universe is the grain growth that is the primary formation mechanism for dust, and it affects the dust to metal and dust to dust ratio. Now the second question is about the evolution of dust content in galaxies. So to do that, this is the same figure as before. So this is the dust mass in the ISM versus stellar mass. And I drew an arbitrary line at dust per stellar mass 1%, which is shown in the red line, and define galaxies above this line as the dust rich and below this line as dust poor. But again, this is only like dust in the ISM. Now, in the ISM dust poor category, we also find galaxies that has massive abundance of dust in the halo. So this galaxies is further described as halo dust rich. So there are like 2 categories in the ISM dust poor. There's like halo dust rich and dust poor, which is like doesn't have dust like anywhere in their system. And I divide to see the evolution, I divide the ISM dust rich group based on their specific star formation rate. So using Milky Way as a threshold, like below that, I define it as quench, and above that as star forming. So what I want to see is how the galaxy properties change in this 4 category. So in this plot the y-axis, the left y-axis is the bulge to total mass ratios, which represent the morphology of galaxies, so like disky, and ellipticals. Now, the x-axis is the specific star formation rate. The color will show the gas phase metallicity, and I show further trend. So there's like 3 mass bin, stellar mass bin. So 9 to 10 in log scale, 10 to 11, and 11 to 12. There are 2 panels here. The lower panel will show the ISM dust-rich group, which is binned by this 3 mass bin. So this is where the star-forming ISM dust-rich resides. So like disky, like high specific star formation rate and relatively high gas phase metallicity. And here's the quench ISM dust-rich, which have even higher metallicity than the star forming, but by definition, it's like has lower specific star formation rate. But both of this group lays in the disky region, while if we see the ISM dust spore, it resides in like a very different place. So it's like more ellipticals, low metal, so it's like very metal poor, and low specific star formation rate. So if we see this like because in conventional galaxy evolution theories, like we imagine galaxies to evolve from this region to this region, right? From the late type population to like early type. And the dust spore, so this is like the poor dust spore, there's no dust here. And we see that the galaxies also evolve from being ISM dust rich to ISM dust poor if we follow the galaxy evolution theories. Now, I'm interested in the halo dust rich group because in the model, there's only dust, like the dust production only occur in the interstellar medium. So this dust is blown up with the feedback mechanism and trapped in the halo. So here is the outflow rate. I think this is only supernovae outflow rate of like the 4 galaxies. So this is the probability distribution. And we see that, so the green line here is the halo dust rich group, which has higher distribution in the high outflow rate than the other group. So these galaxies have like very efficient outflow. And if we look, so here is a cold gas per hot gas mass. So this is cold gas in the ISM per hot gas in the halo. So the green line, the halo dust rich group, peak at the lowest value, which shows that they also have massive gas in the halo. So it means that their potential well is deep enough to trap like the outflow material that is like brought by their feedback. Yeah, so this work has been submitted and is under revision. So the takeaway message is that we saw an evolution in the dust content of the galaxy, while the ISM dust rich groups that we defined before represent the late type population, and the ISM dust poor group represent the early type populations in our model. So the third question is about how this dust shaping the SED. So I made a new Python pipeline called Mentari, which can construct UV to infrared SED from any galaxy formation model. So the SED model is also available in my GitHub repo and is under heavy development now. I'm currently working on this. So if you have any output from galaxy evolution model, you can check it in Mentari and it will show. I'll give you a full theoretical SEDs. And so the first, the motivation of why do we need theoretical SED model. So this is, I'm lucky enough to attend the SED meeting, CANDELS SED meeting in Riverside in 2018, and where people talked about a lot of SED code. And this is from the CANDELS paper, this table. And we see that a lot of code use parametric model to prior the star formation history. And yeah, so they mostly use the late tau model, other model to describe star formation history, but I think that because now we have a more realistic star formation history, I think we should try to move to that direction to construct SED using a more realistic star formation history. Also, many models still use like a dust attenuation, like Kel said, like 1 parameter and 2 parameter dust attenuation curve, which may or may not reflect the total dust content of each galaxies. And because the model can compute the like self-consistent dust mass for each galaxies, then I will try to do that to derive the dust attenuation and use that to compute the dust emission. So there's still many models that doesn't include the infrared emission. So here is the parametric star formation, like the parametric star formation history looks like for like different type galaxies that is used to to infer like different shape of SED. So for example, elliptical, it dies really quick to explain this type of SED. In early type spiral, it has longer time scale. In late type spiral, it's like almost constant. In with and to explain irregular, like random burst is like occurring, like is model to occur. While here is the star formation history from DUSTICITY. So this is an example from one elliptical galaxy, and we see that it looks nothing like the parametric form. So although it's like it has died, I think like 8 giga-years ago for these galaxies. When the star formation rate, like when the star formation still happened, it consists of random number of bursts, like different number like bursts with different intensity and different duration. We can see it more clearly in the spiral galaxy, which still happen till today. Like the star formation still happens till today, and it consists of like many bursts, star formation bursts, and with different intensity and different duration. So using this like history, I couple it with Brujual and Charlot stellar population synthesis, and the orange line is the result. So this is only stars, so this is only stellar spectra. The blue line is the observed SED of a galaxy. So I extract it from Michael Brown paper. And in elliptical galaxy, it looks, I think the agreement is good. While I did not do any fitting here, I only picked like one model galaxy with properties resemble the observed one. But in spiral, because it has like lots of dust, of course, I haven't deal with attenuation and emission here, so it looks very bad. So there's no fitting process here. So to model the dust attenuation, so to derive the dust attenuation, I use Charlotte and Fall model. So this is a two-phase model where dust is consists of the diffuse ISM. So the diffuse ISM attenuates the light for both old stars and young stars, and there is the dust in the birth clouds that only attenuates the light from young stars. To model the parameter of the diffuse ISM, so there are two parameters in the model, the optical depth and the power law index. I use a relation from Treyford 19, which couple the hydrodynamical simulation with radiative transfer code, and see that the optical depth and the power law index relates with the dust surface density. So in the top panel, the blue line here is the screen model from Drain and Lee, and the orange model is the slab model from Calzetti. So the hydro galaxies sit in between those two models, and the green line is the observed from observation. Now the power law index also depends on the dust surface density, while the original Charlotte and Fall model used like one single value for all galaxies. So I use this relation. I use the dust surface density from DUSTICITY to compute both the parameters to derive the attenuation from the diffuse ISM. From the birth clouds, I use this formula, which scales the birth cloud optical depth with the Milky Way value, but based on the dust surface density. So here is it's a very preliminary result. So here's the optical depth that we use in DUSTICITY for diffuse ISM, and this is for birth clouds. Now for the infrared templates, I use Dale 2014, which is a 2-parameter model. It depends on the AGN fraction and an alpha. So it describes the dust emission as, so it's a fraction of dust. So there's a dust mass heated by interstellar radiation field U. So there's a power law index alpha. So there's 2-parameter model, AGN fraction and alpha. So for the beginning, I use AGN fraction set to 0. And to compute alpha, first I compute like the total attenuated light in the UV to near infrared from, and then use that to scale the alpha and the total infrared luminosity. So here is how the full SED look like. So this is the same from before. The orange line is the stellar only, blue line is the observation, and the green line is with the new computed attenuation and emission. And again, this is like, there's no fitting. I just like pick one galaxy, like one random galaxy that has properties resembling the observed galaxy. And the luminosity, because I have like millions of galaxies, like full UV to infrared galaxies, then I can construct the luminosity function. Here's the K-band look like. It doesn't look, so the solid line is the stellar only, and the dashed line is with dust. So in K-band, there's like not many differences because basically stellar. For SDSS, I can recover the like all 5 filters. So the dashed line here is with the dust, and the solid line is the stellar only. I'm still working on the infrared. So this is the 160 micron luminosity function, but I think for the beginning it looks okay. I will try to explore more filters and see how it can recover the observation. Yeah, Sandy.
And yeah, sorry. Before you move on too far from this, I just didn't understand the process with the AGN and the little teeter-totter that you're balancing. Could you go over that again? There's a previous slide.
Yeah.
Yes, first of all, what is that little equation? That is DMD, what's that?
So that's the dust mass. So the fraction of dust mass that is heated by interstellar radiation field. So U is the intensity of the interstellar radiation field.
Where does that formula come from? Did you just?
It's from this paper.
From that, okay, all right.
Mm-hmm.
And is that a theoretical formula or an empirical one?
It's an empirical one.
Okay, so then you've got this formula, and then do you have some information about the AGN, or you've tell what happens next? Sorry.
So what happens is like for this work, I set the AGN fraction is 0. So I didn't. So the model has like some grid. So this is like the SED for the AGN fraction 0, 5%, I think, like how many percent, and then I just set it to 0. And then there is like choose by alpha. So if the alpha is this value, and then this is like the set of SED. So to set the alpha, I use like so there's a prescription that connect the alpha with the total attenuated luminosity.
Are you conserving energy? Whatever is attenuated.
Yeah. So this is the energy balance. So I use energy balance principle. So the total attenuated light is used to compute the total infrared luminosity, and the choose of alpha is also depends on the total attenuated light.
And say again how you're choosing alpha?
Oh, there's a prescription, like a relation between the total infrared luminosity with alpha.
Okay, I think I sort of get it now. All right, thank you very much.
No problem. Yeah, so that's the end of my talk. So I'm still exploring the LCD and luminosity function, still working on like different prescription and see how they can infer, like better infer observation. But so far, the takeaway is like it's definitely like, does prescription definitely improve my UV and infrared part of LCD, and more details will come soon. So here's my conclusion, and I am happy to take more questions.
Thank you, Pipit. There is a note by Harry in the chat about a set of templates in the far IR, if they can be of good use to you. Maybe Harry can say a word about it.
Well, so I think the Dale ones don't have a dust mass scaling, and these ones do. Of course, they're based on models, so, you know, caveat emptor, but, you know, might be worth a try.
Thank you.
I had another question. So since you're using SAMs, you have lots of things that you can dig into, and it seems like the dust, you know, how long the dust lasts in the halo after a starburst would be an interesting thing to explore, because it's something in principle you could try to diagnose with observations. And I tried years ago to do this with galaxy counts behind post-starburst galaxies and didn't get any signal that was interesting, but still always seemed to me to be one of those things that you might be able to tell you how fast dust is getting destroyed in the halos as it gets out there.
Yeah, definitely. It will definitely improve the sputtering. So because like in the prescription, the sputtering in the halo and ejected, I think is the most uncertain, because there's a very little constraint from observation to that like formula. So it only depends on the virial temperature and the density. And we assume that, so the density is computed by like the total baryon mass in the halo. We assume it to have uniform distribution extended to the virial radius, while CGM and IGM from observation might extend, like might have like different density. So yeah, definitely. Thank you.
There are a couple of questions from Sandy in the chat. Maybe we can take one and then go to Kameshwara and then go back to Sandy or other people if they have questions. But the first would be, where do you get the extinction curve?
Okay, so the extinction curve, let me go back to my slide. So the extinction curve is a power law. So this is from this work, Charlotte and Fall 2000. So the formula, I think, is the this one. So this is the formula. I have it here, but this is the ISM. So the optical depth is in, yeah. So the optical depth is the based on this. So this is the optical depth at 550 nano, and then with this power law index, and then sorry, yeah, and to attenuate, it's just like the stellar light times E with this power, with this optical depth. So it depends.
I just wasn't understanding how you actually applied the Charlot and Fall prescription to, you know, different reddenings to young stars versus old stars. Are you doing that?
Yes. So the young stars and old stars would depend on the star formation rate. So using the star formation rate, then we can infer how many like let me see. So in the semi-analytic model, we have instead of star formation, there's like a mass of stars born at different episodes. So we have a list of time scale, like list of time step, and each time step has like, so this many times born in this time step, this many times born in this time step. So when we construct the SED, then we know this like the young stars is only attenuated have with the birth clouds and diffuse ISM, while the older stars from previous star formation episode is attenuated with this optical depth only.
And does the actual form of the extinction curve the same for the birth clouds and the diffuse optical depth, or is it different?
The
You seem
formula
to have eta varying here for the diffuse cloud. What do you do about the birth clouds?
the birth clouds is the same, like, but it follows this, so it is scaled by the Milky Way. So it depends on the dust surface density in each galaxies. So this is the prescription for the birth clouds.
I guess maybe I didn't understand what sigma dust Milky Way is then. Oh, this thing. Oh,
That is the surface density. So this is the surface density of each galaxy, and this is the birth clouds, and this is the diffuse ISM. So sigma dust Milky Way is the dust surface density in the Milky Way.
And is the green from observations?
No, it's only from the model. So the green line here is the birth clouds optical depth that we use in the model.
Yeah, I was wondering, could you just say a little bit more about what that is?
Yeah, so I basically scale the birth clouds optical depth with the value of the Milky Way. So Milky Way, the observed optical depth in the Milky Way.
For birth clouds?
Let me think. I think so. So this is formula from this. And yeah, so this is the birth cloud inferred like in Milky Way. And then just scale this dust surface density of each galaxy with the dust surface density of the Milky Way.
Huh. Okay. So you think if I looked at those papers, I'd see birth cloud extinction curves for the Milky Way?
I'm not sure, but
okay.
I will dig it in and answer it for you.
Okay. Thank you.
Shall we take one question from Kameshwara and then go back to the last one from Sandy, unless there are other questions? Kameshwara was asking whether your cut between quenched and non-quenched it's arbitrary, and does it affect your results in any way?
Yeah. So the cut is arbitrary. So the idea is that because we place Milky Way in the place that we know. So it's based on like the Milky Way is like, it's the definition of like, it's, I think in theoretical word, it's like star forming, but not very star forming. So that's why we choose Milky Way. It's just like an arbitrary value. And in terms of like how it changes the answer, this plot. So the Milky Way, I think, is around here. So if it changes, it will like shift the points like for a bit, but it doesn't really change much. So I try using like different value, but the verdict is the same.
Thank you.
Okay, more questions coming from David Koo. Are there any dust distraction mechanisms in the halo CGM?
Yes, there is thermal sputtering for the both dust in halo and ejector so far, which I think is a good proxy for IGM and CGM. It's the animation. Yeah, so we have sputtering in halo and sputtering in the ejector reservoir, which time scale depends on the temperature and density of both reservoir. So it computed different with different values. So it has different value.
You mind just asking by voice?
what fraction of the dust that goes into the halo and CGM gets destroyed through the sputtering and other processes? Just approximately. Is it like half of it or 10% of it or hardly anything?
It's a very interesting question. I haven't really looked into it. So yeah, I guess I can't. Yeah, so because the dust is brought in the halo by the outflow from feedback, then I have the total dust first before the sputtering, and then yeah, I can evaluate that, but I haven't really looked into it. Thank you for the idea.
I have a sort of ill-posed question. Thinking of infrared luminosity as being used both as a proxy for dust and as a proxy for star formation. I wonder if looking at trends with infrared luminosity could be revealing in the sense of trends of dust inferred from the optical SED versus LIR, or trends in metallicity versus LIR, basically just sort of making a connection between your models and what the infrared demographics of things are when broken down by LIR. Seems like it might be a way to dig into whether you're actually getting the phenomenology that you see when you look at infrared samples.
Yeah, definitely. Yeah. Yeah, I hope with the more SED work, so then I have the so now from the model it only have masses, so that's why I'm looking more to translate it into luminosity. So hopefully with in upcoming months when I finish working with the with the light works the luminosity, then I can use it to compare more observations. So it has it's comparable instead of just translating it to dust mass, which has lots of assumptions. Yeah.
There's a paper by Kate Rowlands a number of years ago that has a title something like "The Dust Crisis in Submillimeter Galaxies," where she points out that the dust masses that you infer from SED fitting the infrared are just way, way too high given dust production and destruction mechanisms. And I haven't seen that explained. But so it would be interesting. I don't know if your models will have star formation rates as high as those submillimeter galaxies, which are 1,000 solar masses a year or something. So you may just not have them in your SAMs, but if you do, that'd be interesting to look at as well.
What is the name of the paper again? Can you?
The author is Kate Rowlands, Rowlands.
Okay.
And the Dust Crisis in Submillimeter Galaxies.
Thank you.
So I'll go back to the chat, and there was a last question from Sandy, which is very close to what was asked now. Do you ever turn things around and try to derive star formation rate and reddening from real data, which I presume is your next step? But if you want to comment more on that, please do. And then we have another question from David.
Yeah, you're correct. It's my next step. So I tried before, but that's when I didn't have dust in my model. So it's only stellar, and it looks so I think I can't draw any conclusion from that work. So then I decide to work more on the SED part. So work on the proper dust attenuation and emission prescription included, and then I will use it to translate the have more connection with the observed data.
Can I just add a little bit about that? It occurred to me. So there are very strong trends about with purported dust measurements. With SED fitting, of course, people have derived tau optical depths, characteristic optical depths for CANDELS galaxies and also for Sloan. And you can see extreme trends in that number as a function of, say, galaxy radius at fixed stellar mass and star formation rate and versus some inclination and so on. So it would be really wonderful if you could match those trends. But I think you would have to start by remeasuring your own optical depths, just to see if, you know, treat your machinery like an observer and deduce an optical depth the way an observer would for a galaxy. And then is that the right, do you get the right number, and does it have the right observed trends as seen?
Yeah, thank you. Yes, that would be interesting.
Yeah, let's go on. Actually, I don't know if did I read the question, did you match the dust SED fitting models of Samir Salim? I don't think I read that question, but it's related here.
Sorry?
Do you match the dust SED fitting models of Samir Salim? Do you know the work? Yeah. Okay, you haven't tried.
I haven't.
But that's true. It's something to try, because it's local galaxies and with a gigantic sample. And the other questions by David was, do the galaxies in Dusty Sage have 3D structure so that SED depends on viewing angle and inclination?
Yeah, thank you for that question. Sadly, no. So the semi-analytic model treats galaxy, because there's like millions of galaxies and we want the model to run fast. So each galaxy is this only like one point that has like one value of stellar mass, one value of dust mass. So we don't have like a resolved structure of the galaxy. We have bulge and disk, and we can differentiate like the mass, like the masses in bulge and disk, but that's it. We don't really have a 3D structure, but a hydro will be, yeah.
Yeah, I'm so sorry. I had assumed that the SAMs would not have anything except bulge and disk, but I thought that you said something about a Dusty Sage was also compatible with Millennium, right?
Yeah.
Yeah, and that does have 3D structure, I believe. But I didn't know whether you are able to take advantage of the 3D, because I'd love to know the dispersion in the properties at a given mass and a given shape and size, etc. That would then really help us observers. Related to the question of translating your work into real observations that we might see. All right, well, thank you.
Thank you.
Okay, I think I read all the questions, and Harry reported the paper by Kate. Yeah, I think I read all the questions. If there are more, please unmute yourself and go ahead.
Oh, I always have more. Out of curiosity, would you be considering in your model? Could you consider your model taking advantage of theoretical work on grain size evolution, and therefore then have sort of different SEDs? I mean, it sounds like you have all the called subroutines in our old language, but whatever it is, you have a little package that you could do something like that. Is that something under consideration? Because I think that might be interesting. The conditions back in time is very different today, and I imagine that grain size might be different, say, of Z2, and especially in the centers versus today's galaxies.
That's the thing I wrote in my postdoc proposals.
Oh, so I see. I didn't see yours. Sorry. Okay.
No. So that's the grain size distribution is like really important, I think, to derive the infrared emission and also the attenuation. Also inside the dusty stage, inside the model, the grain size will like differ. So for now, the AGB and supernovae dust formation, I just put them in one box. But with the grain size distribution, then it will, like, we can see the grain size from the growth will be like, I assume it will be larger than the AGB grain. So it will be a really interesting topic to discuss next. But it will be like I think like it will be on my postdoc. It will not be in my PhD.
Sure.
Study, yeah.
I have more. If you have more.
Let's see if somebody else have other questions. We are almost at the hour anyway. Otherwise, David, go ahead. Take the last one.
Well, just out of curiosity, we Sandy are struggling with issues of dust and wonder whether some some portions of the star forming region might be so obscured that they're basically invisible. So that, it's like totally dark, or some other cases where it serves like a gray, equivalent of gray extinction as well. Do you have evidence in your modeling that some galaxies actually are so obscured that big hunks of their light is totally extincted and therefore would be distorted in that sense?
Yeah. So that's a question I am exploring right now.
Okay. Okay.
So because I'm just like currently translating the mass into light, then there's like a lot of things that I start to looking for. Like for example, that how many galaxies is like very obscure. Like what is the statistic? So yeah, I haven't really looked at it, but I plan to do it like in the upcoming.
Thank you so much. We look forward to your next round for more answers. Thanks.
Yeah, thanks for very nice work. I really enjoyed this talk.
Yeah.